Welcome to Introduction to Geology. I'm Dr. William Patterson, and in this video we'll be talking about sedimentary structures and the formation of sedimentary rocks. Sedimentary structures are features that are formed at the time of deposition. They include bedding, which is the stratification of rock into horizontal layers, cross-bedding, the movement of particles by transport agents, usually water or wind, graded bedding, as currents increase and decrease in velocity, the size of the particle will increase and decrease, and as they're deposited, those grain sizes will change depending on whether the current is increasing or decreasing. Ripples are a superficial representation of this bedding. And bioturbation structures. Animals and plants introduce or disturb sediment prior to lithification. Starting with cross-bedding, here we have a couple different environments. We have a desert environment where the lack of water implies that wind is going to be the main transport agent, and beaches where water is going to be a transport agent. Starting with the wind or water current, if it moves more or less in the same direction most of the time, you will have asymmetric beds. Essentially what we're doing is we're forming layers of sediment as grains saltate or bounce and roll across the surface. They reach the lee slope, they slide down, and they're deposited. At the same time, wind and water is scooping or scouring this previously deposited sediment and moving it into a new dune. The result is, as these layers accumulate, we see a sequence of crossbeds. Now, if the currents move back and forth regularly, we're not going to see this asymmetric form. We're going to see a symmetric form here. So the water washes back and forth, back and forth. It moves these grains back and forth. The result is, if the currents move back and forth equally, we'll have perfectly symmetrical waves. The slopes will be the same on each side of this accumulation of material. So again, the asymmetric ripples that we would see in dunes, for instance, are formed because currents tend to have a persistent direction. Interestingly, if we go from the modern to the ancient, what we can do is reconstruct the direction of the current in the past, whether it's wind or water. And this plays into how the Earth's climate system worked in the past at a given location. At this location, we have some idea as to which direction the currents were moving and how strong those currents were. Bioturbation structures include burrows, where animals are digging their way through the sediment pile, and they may be reinforcing their burrow with some kind of mucus, some kind of agglutinating substance, or just the presence of organic matter within this burrow may result in a slightly harder material that's preserved in the fossil record. Other examples include Cruisiana, which is more or less a trilobite taking a cruise. As this trilobite cruises through the sediment, or on the sediment, it leaves distinctive trackways behind related to its legs and its feet. Sedimentary structures include bedding sequences, which are vertically stacked layers of sedimentary rock with different types of sediment or sedimentary structures in each layer. So slight differences in grain size or grain composition will result in layers that weather out more easily. So that's where you see these apparent gaps in the surface. This material was easier to weather than this material. And that can result from the original material as it's deposited or a diagenetic effect later on, as we'll see in this video. So an example of a bedding sequence is seen here. If you were to head out to this point bar in this small stream and dig a trench, this is what you'd see in cross-section. So this is in one location, one small location, a dramatic change in the appearance of the sediment. Some of this variability in appearance is due to the addition of more or less organic matter. More organic matter makes the sediment darker. Less organic matter usually means the sediment appears lighter in color. Also, the current strength. The current is going to be strongest here at the outer edge of the curve as opposed to here at the inner edge of the curve. It's moving faster here. So it's transporting larger grains, which would include gravel in this case. As we move up sequence, the river gets calmer and calmer as this curve increases. So as that water calms down, as it flows more gently, more slowly, finer and finer grain material is deposited. If that current is consistent, we're going to see asymmetric beds. If it varies back and forth, you'll see deposits more like this. And eventually, when the water is really quiet, you'll see deposition of mud and silt with little indication of current. Burial is the preservation of sediment within a sedimentary basin, whereas diagenesis is the physical and chemical change that converts sediment to sedimentary rocks. Here we see some examples from my master's thesis in Florida, where we're looking at preservation of sediment within a sedimentary basin, and we're looking at the original chemistry of these sedimentary grains. So here I'm swimming with my dive gear, which is hooked to a big block of sediment that you can see here back in the lab. And what I was doing is collecting these blocks so that we can analyze the chemistry of the fluids within this sediment pile. And you might wonder, why would anybody do that? It's because we use this material to determine how much carbon dioxide was in the atmosphere through Earth history. And it turns out that these modern carbonate grains that are precipitated in this environment are not recording a global signal. They're recording a local signal. That might seem obvious now, but it was not obvious when I was a student. So lithification, in turn, includes compaction. We start here by depositing some clastic grains off the coast, somewhere on Earth or Mars previously. These sediment grains are going to be piled up. As they're piled up, they're compressed by overlying material. That compression results in a squeezing out of water. That squeezing out of water, or dewatering, as it's called, is going to force these grains closer together. So this material can lose 40 to 50% of its water merely by compaction. Now this serves another purpose. It brings these grains closer together. And because they're closer together, a slight increase in ionic strength in this pore fluid can result in cement forming. In this case, we have calcite grains growing between these sand grains, which ultimately leads to lithification. The rock becomes hard. Now, different types of sediment are going to result in different sedimentary rocks. If we look at grain size only, going from fine to coarse, the finest grains are muds. These muds are generally made of very tiny clastic particles or clay minerals. When compressed and dewatered and lithified, they become the rock known as shale. Sand-sized grains get compressed, compacted, and cemented together to form a sandstone. These sandstones most commonly have cements made of calcite or quartz. That's something that's very easy to determine with a little bit of 10% hydrochloric acid. Just drop it on a sandstone. If it fizzes, you got a calcareous sandstone. If it does nothing, then you most likely have a quartz cemented sandstone. Moving up in grain size to the gravels, when the gravels are compacted and cemented together, they become a conglomerate if they're rounded grains. If they're angular grains, we call this same rock with the same clastic size a breccia. If we're looking at organic matter and formation of rock from that organic matter, we can start out with diatoms. By cooking these diatoms to the right temperature for the right amount of time, we can create oil and gas. This oil and gas would be hosted in a diatomaceous material. If it's plant material we're looking at and we compress it, we're going to form what's called a lignite. That's kind of a junky coal. It doesn't have much energy. It's light and fluffy. If you compress and heat that coal, you can get what's known as anthracite, the king of coals. That's dark, hard, has kind of a conchoidal fracture to it. That's the coal that's worth big money. Now, cementation is going to occur again, once those grains get closer together. And what we see here are quartz sand grains that are cemented by calcite. So this is a thin section where we can see the pleochroic nature of the calcite minerals growing between these clasts. Taking a little closer look at these rocks, we're going to talk again about particle size. So the fine grain material, clay-sized material, forms shale. Sand-sized grains form sandstone. And that sandstone is going to be given a name based on what the grains are made of. The same thing goes with a conglomerate. So much larger grains here, cobble, pebble-sized grains, again, rounded, called a conglomerate. In the UK, called pudding stone. This is how we classify a clastic sediment rock based on size. Coarse grained, larger than 256 millimeters, is called a boulder. 256 to 64 millimeters, we have a cobble. 64 to 2 millimeters, a pebble. Most of the rocks you'll see are within this grain size range for conglomerates. Medium grain clastic rocks are made of sand. Sand-sized grains range from 0.062 millimeters to 2 millimeters. These are visible. Even the very fine grain material is visible if you hold it to the light just right. So the result is a sandstone. And the sandstone, again, is going to be given a further name based on what those sand-sized grains are compositionally. And the fine grain rocks include muds, which can be silty, resulting in a siltstone, or if they're really fine grains, less than 0.0039 millimeters, we're in the clay size range now. So clay is both a type of mineral and a particle size. So we need to keep that straight. If you make a rock out of clay, it can be a mudstone if it's got a blocky fracture, a shale if it breaks along bedding, or a claystone, which has no appreciable structure. Taking a look at the four major compositional groups of siliciclastic sediments, we'll start out with lithic sandstone. Lithic implies rock, so this is sandstone that includes sand-sized rock fragments. So these chunks of stuff here in green represent little bits and pieces of rocks, whereas these other grains represent mineral grains. So this would be quartz, and these would be feldspars. So this is going to typically be formed in a delta environment where we got a lot of junk flowing down a river. In the case of an arkose, this is going to be a sandstone that has a significant amount of feldspar. These generally form in arid regions because if you add water to feldspar, you get clay. It chemically weathers to clay. The lack of water implies that the weathering is all going to be physical. Again, an arkose is a feldspar-rich sandstone. Many of the grains are sand-sized feldspar grains. A quartz arenite is a pure, clean quartz. It's been through the washing machine a number of times. It may have originally formed as a granite. That granite got weathered into a lithic sandstone. That lithic sandstone got weathered again, spending a lot of time on the beach. And the result is we weather away all the minerals except the most resistant quartz. And turbidity currents, or submarine fans, are composed of a mixture of stuff. These are called gray wacky, which kind of means gray junk. And this is a case where we're taking material that's been deposited from a delta and washing it rapidly downslope into the deep sea in a turbidite current that forms a submarine fan, like the Bengal Fan and the Indus Fan. So the arkose again is going to be feldspar-rich sandstone. If the sandstone contains sand-sized rock chunks, it's lithic. If it's pure quartz, it's a quartz arenite. And if it's a mixture of stuff, lots of stuff, it's a gray wacky. Which brings us to a question. What does sedimentary rock have to do with Anheuser-Busch locating its world headquarters in St. Louis? Well, there's a lively German community in St. Louis, but what it takes is more than a lively German community. It takes rocks, and rocks are required for Budweiser. So here we have the St. Peter sandstone. This is a 450 million year old sandstone that formed on a beach during the Ordovician, which is now where St. Louis is located. If you take a close look at this, it is a really nice, clean, pure quartz arenite sand. And this quartz aranite sand, very clean sand, is very good for making glass. St. Louis also has a nickname, the Mound City, and it's called the Mound City because early Native Americans built cities on mounds throughout this region. St. Louis is over here, East St. Louis here, and Cahokia, Illinois here. This is the site of the famous Cahokia Mounds, a very, very large pre-Columbian structure that was the centerpiece to this city. These mounds are made of clay that is scooped up from the floodplain of the Mississippi River. So the people took this clay and built these architectural wonders from that clay. And Budweiser said, hey, these mounds are clay, and we can use them to make beer holders, ceramic growlers, and ceramic bottles, or glass bottles. This is a Budweiser bottle from around 1880, made from the St. Peter sandstone.
Here comes the king, here comes the big number one. Budweiser beer, the king is second to none. Just say Budweiser, you've said it all.